In this video, we're going to look at the derivatives of general, exponential, and logarithmic functions. So we're going to start first with derivatives of logarithmic functions with any base. So recall the change of base formula. Log x base a is equal to log x base b over log a base b. This formula can be used to differentiate functions with bases other than Euler's number e. However, we will use properties of the natural logarithm to help us differentiate these functions. So on the left side, I'm going to do an example with base 2 and the argument x. All right, so this is different than what we did in the previous lessons. In the previous lessons, we were looking at base e, okay? And then on the right side, I'll just do the general case. So let's start over here. We are going to use the change of base formula, all right? And so I'm going to rewrite log base 2 with the argument x, and I'm going to rewrite that using the base of Euler's number. So log x base e all over log 2 base e. You may recall that anything that has e, or any logarithm that has e as its base, we can rewrite as the natural logarithm of x all over the natural logarithm of 2. So this is how I can rewrite log x base 2 using the change of base formula. So I'm going to rewrite this function right here. Y is equal to log base 2x. Then since I know that it's just this, I can rewrite it as ln x all over ln 2. I recognize that the natural logarithm of 2 is just a constant. It's actually just a number. So I can treat that as a coefficient, 1 over ln 2 times the natural logarithm of x. And so I differentiate both sides with respect to x. So dx of y. And then this is a constant multiplier, so I don't have to worry about taking its derivative, and then d dx of ln x. So d dx means take the derivative of y with respect to x, take the derivative of ln x with respect to x. Well, the derivative of y with respect to x is just the derivative, right? It's the first derivative. This over here is the constant multiplier. And then I already know this from past lessons that the derivative of the natural logarithm of x is simply equal to 1 over x. So I can just rewrite this as follows. dy dx is equal to 1 over x ln 2. Okay, so over here, that's my argument. And this right here was the base of the logarithm. So the general case for this can be done as follows. It's saying, okay, well, find it when y is equal to log base b of x. Well, again, I can just rewrite this using the change of base formula. Y is equal to ln x all over ln b. And then I take the derivatives of both sides. And I know that 1 over ln b is just going to be a constant times the derivative of ln x, right? So then the derivative in the general case is equal to 1 over the natural logarithm of whatever the base of the logarithm was times 1 over the argument, all right? So my general case is dy dx is equal to 1 over x ln b. All right. Now, you'll see this written over here, okay, as a general case. But we also have to consider, what if the argument itself is a function? Well, if the argument itself is a function, then I have to go 1 over the argument times the ln, or the natural logarithm of the base, but then I have to chain rule with the derivative of the argument. So in this case, the outside function is the logarithm and the inside function is u at x, so the chain rule is used. Another way of looking at this is just this right here. This right here is simply the derivative of the argument, so the derivative of the argument will go in the numerator over the argument itself times ln of the base. So it might be helpful to see some examples of this, okay? So as you can see right here, I have my argument here is a quadratic, right? So that's my u at x, right, is equal to x squared plus 1. But my outside function right here is the logarithm base 8. Okay, so I'm going to take the derivative of my function here. And so the derivative of the function, recall, is going to be 1 over the ln, the natural logarithm of whatever the base was, in this case it was 8, times the argument, but then I have to chain rule that with the derivative of the argument. So I can then rewrite this simply as, again, the derivative of the argument all over the natural logarithm of the base times the argument. Again, the order doesn't really matter. You could put the argument first and the derivative, or sorry, the natural logarithm of the base on the other side doesn't really matter. Okay. It says differentiate this function right here. It may be useful to identify b and u at x. You can also use the logarithm rules you learned in the past to help with the exponent on the argument of the logarithm. So that's true, right? I can rewrite this as simply 4 times the logarithm base 5 of x squared plus 3x. So I know that my base in this case is going to be 5, and my argument is x squared plus 3x. So the derivative of my argument is 2x plus 3. And then I can just apply the formula that I saw on the previous page. Remember, I'm going to have 1 over the argument times ln of the base times the derivative of the argument, right, using the chain rule. So right here, the first derivative is equal to 1 over the argument, which is x squared plus 3x. I'm going to put that all in brackets, times the natural logarithm of the base, which is 5, and then times the derivative of the argument, which is 2x plus 3. And then I can put that in the numerator, 2x plus 3 all over ln 5 times x squared plus 3x. This next example looks more complicated than it really is. We can just simply rewrite this using some of our logarithm rules that we know. Okay, so this is really just saying x over x plus 2 raised to the power of 1/2. I bring that in front as a coefficient. And then I have to recall that I can use my logarithm laws right there, and I can say log base 7 x minus log base 7 bracket x plus 2. Okay. Constant multiplier, I don't need to worry about that. So I'm going to say 1/2 right there. And then I'm going to take the derivative of each of these inside functions. So this one right here, so I'll just continue with my square brackets, is going to be 1 over x ln the base, 7, minus, same thing over here, 1 over x plus 2 ln 7. Okay. I can recognize here that since the natural logarithm of 7 is common to both of the denominators, the only difference in these denominators is this one has an x and this has an x plus 2, so I can get a common denominator. Okay, and so I need to multiply this fraction by x plus 2 over x plus 2. So that means that this is going to become right here x plus 2. Right, and then in this one right here, the only thing that I'm missing in the denominator is an x, so I'll multiply that one by x. Right, and then I will have a common denominator of x plus 2 ln 7. Hopefully you can see that the x's will cancel because x minus x is equal to 0. So then I'll only be left with a 2, but then I have this multiplier of 1 over 2, so that 2 will cancel. And then we will end up with the final answer, which is 1 all over x plus 2 ln 7. So now we're going to look at derivatives of general exponential functions. So these are general exponential functions that don't have base e, all right? But we're still going to use Euler's number to help us find the derivatives of these. So again, I'll start with an example with a very specific base, that's base 2, and then I'll do the general case, base b. So the first thing I'll do with this right here, y is equal to 2 to the power of x, is I'm going to take the natural logarithm of both sides. And this allows me to bring then the x down in front as a coefficient using our logarithm rules. All right, well now what I'll do is I'll take the derivative of both sides. So I'll take dy, right? I can't take the derivative of x first because it's in terms of y, but I can chain that with dy dx, right? And then over here, ln2 is just a constant multiplier, so I can just do that. And then dx of x right there. Okay, so I know that the derivative of the natural logarithm is 1 over the argument, and then I've got this right here, dy dx is equal to ln2, and then this right here I know is just simply 1. Isolating for the derivative, dy dx is equal to, and I can take both sides and multiply by y. So then I get y ln2, and I know I previously defined y as 2 to the power of x, so therefore the derivative is equal to the exponential function again times the natural logarithm of the base. So that's with a specific example of a base 2, but can I do this for base b? Well, absolutely. Again, I'm going to take the natural logarithm of both sides. That allows me to bring the x in front. And this right here is a constant, so I'll just put that in our notes right there. Right. I can't take the derivative of this with respect to x. I first need to take the derivative of this with respect to y, and then dy dx. And then this is a constant multiplier, and then d dx of x. This is 1 over y, dy dx is equal to the natural logarithm of the base times 1, dy dx is equal to y, natural logarithm of the base, and then dy dx is equal to the exponential function again times the natural logarithm of the base. Okay, so I think I've summarized this below in the notes. Let's just scroll down and see. Yep, right here. And again, one of the things that you have to be mindful of is you could have a composite function whereby the exponent on the exponential function is in and of itself a function. So if that's the case, then we have to do the exact same thing that we normally do. We do the natural logarithm of the base times the exponential function, but then we have to chain that with the derivative of the exponent. Okay, and we'll see that right here, right? Use the above to differentiate the following functions. Okay, so I know that my formula right here says, okay, so if I look at this, it says y prime is equal to the natural logarithm of the base times the exponential function again, but then times the first derivative of the exponent. So I can apply that rule. I don't have to do this from first principles. The base here is 5, so ln 5. The exponential function is 5 to the power of 8x squared, and then the derivative of the exponent is 16x. The next example involves us using the chain rule, and something that I like to do is I like to define the top one as like, we can call it whatever we want, but I'm going to call it f of x is equal to 2 to the power of x, right? And then I'm going to find the derivative of that, and the derivative of that is just ln 2 times 2 to the power of x. And then I have my denominator function, g at x. And my denominator function is x plus 1, and the derivative of my denominator function is just 1. And the reason why I set this up right here is so that I can go ahead and I can use the quotient rule. And so the quotient rule, if you recall, I'll just write it out over here. The quotient rule is the derivative is equal to the derivative of the numerator times the denominator function minus the derivative of the denominator function times the numerator function all over the denominator function squared. Okay, so let's go ahead and now that we have all this information already done for us, I can just sub this in to the quotient rule. So the derivative of the numerator is just, ln 2 to the x times the denominator function, which is x plus 1. And then the derivative of the denominator function is just 1 times the numerator function, which is 2 to the x. And then the denominator function is x plus 1 all squared. Okay, I can clean this up because I can recognize that there is 2 to the x in both terms. So I can factor that out. 2 to the power of x, and then open brackets, ln 2 x plus 1 minus 1. Close those brackets, all over x plus 1 squared. Moving down to this example right here, this just simply involves using the product law. So I'll find the derivative of the first, and usually when I've been doing product law, I've been color coding it. So the derivative of the first is just natural logarithm of 10 times, again, the exponential function again. And again, the derivative of the exponent here is just going to be 1, so I'm not going to worry about that, multiplied by e to the x, plus, and then again, I write the first function, 10 to the x, and then the derivative of e to the x, we recall from our first lesson, is just simply e to the x. Looking at this right here, I can see that 10 to the x and e to the x are common to both terms, so I can factor that out. 10 to the x, e to the x, open bracket, ln 10 plus 1. Okay, in the final one right here, this is just a chain rule example because I have an exponential function and the numerator, or sorry, not the numerator, the exponent is in and of itself an exponential function. So I've got an exponential function of an exponential function. So let's use our chain rule. Okay, so y prime, okay, I'll just do this right here is going to be ln 8 times the derivative, times the original function, and now I need to take the derivative of the exponential function or the exponent, and the derivative of the exponent is simply just e to the x again. And so there we go. That literally is the answer to that question. Okay, homework is listed there, and thanks again for watching.